Hi, it's Keith Bates here, and today I'm going to try and explain Merkle trees, what they are, what their purpose is in blockchains, and I'm going to use an analogy. So imagine a fictional Nordic country called Bitcoinia, where all the residents are obsessed with the law, and the laws that are passed by Parliament or that arise from case history out of court decisions are bound in books. And the funny thing is that those books are the law, and if somebody can tamper with one and say add a rule that says that Gary is allowed to rob banks, then anyone called Gary is allowed to rob banks. So criminals could tamper with the laws in order to get away with their crimes. So the residents have come up with a very clever scheme whereby they can protect these books from tampering without it requiring an immense amount of effort. Now, the first thing is they've got an amazing machine that you can feed the text of a book into, and it produces basically an ISBN number that you can stick on the book. But the ISBN number that is produced is unique to each different form of text. So if you take a book and you change one letter in the book and you put it into this machine, you get a totally different ISBN code out. And the second thing about it is that you can't engineer a book to give you a specific ISBN code. They're almost random in that respect. Now, what the inhabitants of this country could do is they could put all the books in a library, and then they could gather all the text from all the books, feed it into the machine and make one code, and that would ensure that later on they could repeat the process, do it again, and if the code matched, they'd know that all the books were intact and no one had tampered with them. But this is terribly inefficient because it means that you have to go and collect all the books from all the different rooms. It's just not feasible. So instead they've taken the following approach. They group books into pairs. Each book is run through the machine and gets its own code, which is put on the back of the book, and then two books are put on a shelf, and the ISBN codes off the back of those two books are concatenated, that means added together, one after the other, and that new code is fed into the machine to get yet another code, and the shelf is labelled with that. Now, each bookcase has two shelves, and they repeat the process. They take the two codes off the front of the shelves, concatenate them, put them in the machine to get a new code, which they stick on the bookcase. And then they have two bookcases in each room, and they do the same process in order to get a label for the room's door. And there are two rooms on each floor of the law library. So in order to label the floor, they use the codes of the two doors, and then finally they put a label on the front of the law library that is the two codes from the two floors concatenated and run through the machine. Now, you may wonder, why are they doing this? Well, it's very simple. If there's a court case and it requires the laws from book number 3, they don't have to go and gather up all the books to check it. They take book number 3 and check that it's hash. Take its hash. Now, somebody could have gone in and changed book number 3 and put a new code on it. But what they can now do is they can look at the number on the other book next to it, check that's okay, and that together they hash to the shelf label. And then somebody could have changed the shelf label as well, but then they take the shelf label below and they check again, and then they check that the two bookcase labels give the room number, and that the two room numbers on the floor give the floor number, and finally that the two floor numbers give the number on the front of the law library. And they know the number on the front of the law library hasn't been tampered with because they have security cameras pointing at it all the time. And that way, they don't have to retrieve all the books from all the rooms in order to check that one little change has occurred in the particular book that they're interested in, which is what you would have to do if you just made a code from all the books together. So basically, what I've described is a Merkle tree. And should be pretty obvious, in things like Bitcoin, the books correspond to transactions, and the code on the front of the library is what's called the root of the Merkle tree, which is stored in the header, and then the headers are locked together in the usual blockchain way. So that's why Bitcoin uses Merkle trees. That's why Nakamoto decided to put them in there. Ethereum uses them as well. It's a very common practice to allow people to verify a snippet of data has remained intact without having to download lots and lots of what are basically irrelevant transactions. You only have to kind of go up one little branch. So in this case, from the book to the shelf, to the bookcase, to the room, you're not looking at all the rooms, you're not looking at all the bookcases. Anyway, I hope that explained it to you. If you have some more questions, please feel free to ask them in the comments below, and I'll see you again in the next video. Bye for now.